Hello everyone, I'm Sirik Nurasul from SE 2525. So I choose fourth and the fifth lectures. So let's start with fourth. Integers. So first exercise is division algorithm. So let's start with division algorithm. So we can see this theorem says that for any integers a and b with b not equal to 0, there exist unique integers q and r such that a equals q times b plus r, where r is between 0 and the absolute value of b. So here q is called the quotient and r is called the remainder. So for example, 19, like we want to find the quotient and the remainder when 19 is divided by 7. So the quotient is 2 and the remainder is 5, because 2 times 7 is 14 and 19 minus 14 equals 5, which is less than 7 as required. So that's answer. So second division algorithms с отрицательным числом. So now let's try a trickier example with a negative number. So we divide negative 1027 by 38. Even though the number is negative, the remainder must still stay positive and smaller than 38. That's why the quotient here is negative 25 and not negative 27. We need to keep the remainder inside the correct range between 0 and 38. So third. So in the third, we actually doing the exercise Euclidean algorithm. So now let's talk about the greatest common divisor, or just like GCD, the largest number that divides two given integers. We can find it quickly using the Euclidean algorithm. So the idea is to divide repeatedly each time. We use the previous divisor and the remainder to make a new division. And we continue until the remainder becomes 0. So the last non-zero remainder is the GCD. So let's find the GCD. For example, 630 and 196. Yeah, that's for example. So we start like that. We're starting like that. So we stop once the remainder equals 0. So the last non-zero remainder was 14. So GCD, this GCD equals equals to 14. So that's lecture 4, and the next step is lecture 5. So it's an induction and a recursion. So first exercise, mathematical induction. So mathematical induction is a method that used to prove that a statement is true for all natural numbers or all integers starting from some given number. So there are two steps. First, we check the base case, usually n equals 1. So the second, we assume the statement is true for n equals k. So this assumption is called the induction hypothesis, and then we prove that it must also be true for the next integer, n equals k plus 1. So let's prove that for every integer n greater than or equal to 1, so the sum of odd numbers, so for example no, not like that, 1 plus 3 plus 5 plus so on up to 2n minus 1 equals n squared. So step 1, the base case, when n equals 1, so the left side is just 1. So in the right side is 1 squared, which is also 1. So the base case holds. Step 2, the inductive step, we assume the formula is true for n equals k. So 1 plus 3 plus so on 2k minus 1 equals k squared. That's induction hypothesis. We need to show it's true for n equals k plus 1. We take the left side, and by the induction hypothesis, the sum up to 2k minus 1 equals k squared. So we just add the next odd number, which is 2k plus 1. So and indeed k squared plus 2k plus 1 is exactly k plus 1 squared. So the statement is true for k plus 1 as well. By the principle of mathematical induction, the formula is true for all greater than or equal to 1. So the next, should be 1. So the second size, recursive sequence, or just a Fibonacci term. So now let's talk about sequence defined recursively. Recursive definition gives the first term or terms directly, and then a rule to find every next term from the previous ones. The most famous example is a Fibonacci sequence. It's defined like this. So I can show you. That's a formula. So it's defined like the first two terms are both 1, and every next term is the sum of the two previous terms. So let's compute the first few terms. We start with 1 and 1. So the third term is 1 plus 1, which is 2. The fourth term is 2 plus 1, which is 3. The fifth term is 3 plus 2, which is 5. And continuing this way, we get 8, 13, 21, and so on. So like, so I said 1, 1, 2, 3, 5, 8, 13, 21, and so on. So that's answer. So next step, third exercise. Let's look at one more example. So no, like that. No, like that. Another example. So a sequence where the first term equals 1 and every next term equals 3 times the previous term plus 1. So let's compute a few terms. The second term is 3 times wait. So the second term is 3 times 1 plus 1, which is 4. The third term, so I can show that like this, yeah. First, second, 4, third, 13, yeah, and 40. The first term is 3 times, 3 times 13, and the plus 1, which is 40. So by guessing a pattern or using a method called the characteristic polynomial, we can find the general formula for the sequence is a sub n equals 1/2 times. So I can show you. I can just show you like this. Or just like that. So we can find the general formula for this sequence is a sub n equals 1/2 times 3 to the power n and minus 1. So you can see that. So that's all. That's 5th lecture and the 4th lecture. So that's all.